So in this lecture, we will look at sets and set theory. So we begin with a definition of what exactly is a set. So we say that a set is a collection or a group and it is a collection or a group of distinct. So that means we do not have any repetitions and it is well defined related objects. Okay, so what that means is there must be absolute clarity as to what elements are in the group or the collection, and there must be no ambiguity. Okay. So I have some examples here of collections, some of which are sets. So the first one is a collection of good people. Okay, so if we look at this one, obviously there is some ambiguity here because it's not absolutely clear who belongs to this set or not, so to this group or not. So someone might say, I'm a good person, I definitely belong to this group. Another person would say, no, but you did this, you did that, you're definitely not a good person, you don't belong to this collection. So here, this is what we would say is not a set. Okay, so the reason for that is this word here, good, can be left up to one's own judgment. And what one person considers good is not necessarily what another person would consider good. So another one, we have a collection of vowels in the English alphabet. Okay, so this one is definitely a set because given any two letters, we know whether they are vowels or not. So it's easy to say B does not belong to this collection, but A does, and so on. So another one, we have a collection of lovely flowers. So again, the use of the word lovely is what would disqualify this collection from being a set, because lovely can be up to an individual. So what one person considers lovely is not necessarily what another would consider lovely. Okay, then we have a group of NUST students. Between 18 and 25. So this one here, let me just write, so we say not a set, and this one is definitely a set. So it is well defined. Given any person, I would be able to tell whether that person is a NUS student and whether the person is between 18 and 25, and then I can determine whether they belong to the set or not. Okay. Next, we have a group of smart students. Okay, so a group of smart students, this is not a set, again, because of the use of the word smart. So somebody might say, if you're studying mathematics, that makes you smart. Another person would say, no, you have to be studying engineering to be smart. Another would say, no, you must be studying medicine to be smart. Okay, so there is some ambiguity over there. So that is why it is not a set. Then 3 best surgeons in Namibia. Okay, so again, the use of the word best, unless the criteria for defining best is well defined, clearly stated, this is not a set. And then we have a list of difficult questions in a test. Okay, so again, this is not a set. Why? Because of the use of the word difficult. All right, so difficult is subjective. So I'm sure you've seen this before. When you write a test, you might find one question extremely difficult or challenging, while another person would say that was the easiest question on the paper. Okay, so again, a set, this is a collection, it's a group, it's a list of well-defined, distinct related objects, okay? So these objects are related by this property that they have in common. Okay, now with a set, we have what is known as the elements of the set. So we have elements of a set. So our definition of the elements of the set, we say that the different objects that form a set these are called elements. Okay, so if we look at our collections that were set over here, so we start the collection of vowels in the English alphabet. So A, for example, that is an element of the set. E is an element of the set. If we look at this one here, a group of NAS students between 18 and 25, I think most of you in this MAS class would be elements of this set. Okay, so elements just refers to the individual objects that make up the set. So notice that objects may be letters, they can be numbers, they can be countries, schools, persons. It's not always just numbers. Okay, so it's important to note that these elements are distinct. So the elements are distinct with no repetitions. So when we are writing these elements in the set, we do not repeat any, okay? So just like when I have a class list, I do not repeat or put anybody's name more than once. So you are just one single individual, and then I cannot put you in the set more than once. So with no repetitions, and they must be well defined, of course, otherwise it's not a set. And they may be in any order actually, and they may be written any order. So the order we put them in doesn't matter. So just like when I was talking about the vowels, I could say A, E, I, O, U. Another person would say E, A, I, O, U, and so on. So there is a number of ways that we could write them, and all are correct as long as A is there, E is there, I is there, O is there, U is there. The order that we put them in doesn't necessarily matter. Okay, then we have notation. How do we denote these sets? So the notation that we use. So our sets, these are denoted by uppercase letters. Okay, so usually we'll call it capital letter A, B, C, and so on. And then the elements are usually denoted using lowercase of the same letter as the set. These elements are denoted using lowercase. For example, A. Okay, we have B and we have C. So the set is uppercase A, and the individual elements, we represent them with a lowercase. Okay, and then when we want to show that small a is an element of set big A, we write A is an element of the set A. Okay, so this is to denote A is an element of the set capital A. Okay, so this is a symbol. It looks like a funny E. So it's like a C with a line between them, okay, to make it look like an E. So this means that A is an element of the set A. Then we can also write X is not an element. So if we write the E with a line through it, that means it's an element, but when we cross it out like this, that is to say it is not an element. So we write X is not an element of Y to denote that X is not an element of the set Y. Okay, so these are just some of the notations. Our uppercase letters are used for the set, lowercase used for the elements, and then we use the special symbol, this E, to show that A is an element of the set capital A. And then if we strike through our element symbol, then it means it is not an element of that set. Okay, there are a couple of standard sets that we should just take note of that we will use quite a lot. So the first one is this set, which is denoted with this math bold N. So this is the set of the set of natural numbers. Okay, so this symbol is what we use to denote the set of natural numbers. So we can say that n, this is equal to this set. So these are our set braces that we use, and we could list the elements. We have 1, 2, 3, and it goes on forever. So the dots there represent that it goes on forever. It never ends. We could also write it like this. We say that x such that the dots x is a natural number. So these are two different ways of writing our sets, okay? And then in a few minutes, we will define what is this way of writing or denoting a set, and what is this one over here. Okay, so that is our first set. Then we have the set of integers, which we use this Z. This is the set of integers. Okay, so we know that Z, we can write it where we have dot, dot, dot. It starts at minus infinity. Then eventually we get to -2, -1, 0, 1, 2, and it goes on forever like this. Okay, and then the second way that we can also denote this set of integers is just x such that, so sometimes you will see we use the colon, or we have a line here such that x is an integer. Okay, so these are the two ways of denoting this set. Number 3, we have the set of rational numbers. Okay, then the set of rational numbers, we can only represent it in this way. We have x such that x is equal to p over q, where p and q are elements of the set of integers, because we know that is what rational numbers are. Rational numbers are numbers where, I should of course put that q is not equal to 0. That is very important because we're not allowed to divide by 0, and q is not equal to 0. Okay, so we know that the set of rational numbers, this is a set of numbers that you can write in this form. You have a fraction, your numerator is an integer, so that's what it means. If we say p and q are elements of the set of integers, it means they are integers, okay? So they are integers and the denominator is not equal to 0. Then the next set is the set of real numbers. We have the set of real numbers. And this one, we can only represent it like this, x such that x is a real number. And then we have the set of complex numbers. Okay, so we have C. This is the set of complex numbers. And we can represent it like this. C is equal to x such that x is equal to a plus bi, where a and b are the real numbers, and I is equal to the square root of -1. So in your other courses at some later point, you will learn about complex numbers. So this is just something for you to take note of. Now, these are definitely not the only sets we have. We have the set of irrationals, and the irrationals is just all real numbers, and then you remove the rationals. Okay, so when we start talking about complements of sets, we will find out how can we represent the set of irrationals using the set of reals and the set of rationals. Okay, but these are just 5 that I'm sure by now you are already familiar with. Okay, so now that we know what a set is, what an element is, we've already looked at with these 5 sets ways in which we can represent a set. So we then look at the representation of a set. So how do we present or represent a set? So we say that there are 2 main ways. 2 main ways of representing a set. This is also describing or specifying a set. Okay, so the first way is what we call the roster form. So this is roster. Okay, and this is basically just the listing. Okay, so like with our set of vowels in the English alphabet, if I were to write that in roster form, I would just list them A, E, I, O, and U. Just list them. Okay, so if we look at an example of this, we say that V is the set of all vowels in the English alphabet. Okay, and now we want to write this in roster form. So in roster form, we said we are going to list it. So we say V is equal to A, E, I, O, and U. Okay, and the order we put them in. Okay, so the next one we have B is the set of all letters in the word mathematics. Okay, so if we want to write this in roster form, we would say B is equal to, we have M, we have A, we have T, we have H, we have E. Now we're not going to write M again because remember our set, the elements are distinct. There are no repetitions. I cannot write M again because M is over here. Then next would be A, but it's already written over there. Then T is already written there. Then I have I, and I have a C, and I have S. Okay, so this is how I represent my set in roster form. Elements must be distinct. That means they cannot be repeated. You cannot write the same element twice, even though it is being used twice in the word. It must appear only once. Okay, so I hope that one is clear. Then another one. See, we have the set of whole numbers less than 5. Okay, so with whole numbers, we're talking about natural numbers including 0. So we don't consider the negative. That is the definition of whole numbers. So this set, we're not given a letter to call it. So we can just say A is equal to 0, 1, 2, 3, 4. Okay, so that is where we stop. And this is a set because the whole numbers part, that is well defined. Okay, so it is natural numbers, including 0. We don't consider the negative ones. If we do, then we're now talking about integers. But here we're only talking about the positive ones, including 0. So this is how you would write it in roster form. Then one more, D. We have the set of whole numbers less than 20 and divisible by 3. Okay, so that means we are looking for multiples of 3 that are less than 20. So here we would have 3, 6, 9, 12, 15, 18. The next one would be 21, but it is not less than 20. So we stop there. Okay, so this is what we call a roster form, where you just list the elements. Now, in the case of natural numbers, so we did write our natural numbers in two ways. We go back. This is what we would also refer to as roster form. So this is in a roster form, because the elements are listed. So roster form does not necessarily mean that you are writing every single element. If there are too many to write all of them, write a couple so that we can see that there is a pattern. It's 1, 2, 3, then obviously the next one is 4, and then you put dot, dot, dot to show that it goes on forever. Okay, so another one, if I just wanted the natural numbers from 1 to 100 in roster form, I would just write it as 1, 2, 3, dot, 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 and then 100. And that tells me from 3, I must keep going, and then I stop at 100. But writing it like this means it goes on to infinity. This one tells me that I stop at 100. So that is roster form, and that is the first way, and one of the ways that we represent our sets. Okay, then the second way of representing our set is what we call set builder notation. Okay, now with set builder notation, we use a rule, a formula, or a statement. So it is well defined. Okay, now let's say, for example, we have a set A is equal to 2, 4, 6, 8, 10. This is obviously in roster form because we have just listed the individual elements. Now we want to write this in set builder notation. In set builder notation, we would say X is an element of n. It doesn't actually matter what you call the elements, whether I use small a here or X. I could just as well use a. It doesn't actually matter. So it has elements X or even a, which are natural numbers, such that X is even. So we're looking at describing the elements we have here, and X is less than 12. Okay, so here you look at what you have defined and written here. Does it accurately define or include all of the elements? I have 2, 4, 6, 8, 10. These are all natural numbers. They are all even, and they are less than 12. So this is the way to write it. It may not necessarily be the only way, because with set builder, we're writing a statement. Okay, and with a statement, there are different ways of saying things. Okay, as long as your statement accurately defines what we have here, and there's no room for any other element to be in the set based on your statement. Okay, so you might state it differently, but at the end, we should come up with the same roster, basically. Okay, another one, we say B, this is equal to January, June, and we have July. Okay, so we can clearly see that these are months of the year. And why these specifically? These are months of the year that begin with the letter J. So in set builder notation, we have X is a month of the year. starting with J. Then another one, let's say C, it has these numbers 1, 4, 9, 16, and 25. Okay, so we have these 5 elements. We can see that these are all square numbers. So in set builder notation, we can say C is equal to, it is of course a natural number. All of these are natural numbers. So we're picking elements from the set of natural numbers. And we have X is less than 50. So we don't have any natural numbers less than 50. I mean, here we do, all our numbers are less than 50. And X is a square number. Okay, so that's one way of writing it. All right, so there's different ways, like I said, of writing it. Maybe you would want to write it with a formula. So we say X is a natural number and X is equal to Y squared, such that Y is between 1 and 5. So that's another way. So again, this is just to show you that the way we write in set builder notation is not necessarily unique. So one person may write it complete like this. We have natural numbers. They are all less than 50, but they are all, okay, maybe that is not right. I shouldn't put 50 here. I should maybe put 30 because then 49 would be here. Okay, so I shouldn't put 50. Let me put 30. My bad. Okay, so it's okay, so these are natural numbers. All of them are less than 30 and they are square numbers. If I put 50 here, then 49 should be in there, and that statement would not accurately define the set. Okay, and I stop at 30 because 36 is the next one, and I'm only interested in the square numbers that are less than 30. Okay, I think this one here, the second one, is the most accurate way of describing it, where X is a natural number and it is equal to Y squared. And what is Y? Y is from 1 to 5, and it can only be the natural numbers if X is to also be a natural number. Okay, so that is set builder notation. Let's see, one more. If we say P is the set of natural numbers greater than 12. Okay, so here the set is described, and if we write it in set builder notation, we say X is an element of the set of natural numbers. That means it is a natural number, and X is greater than 12. Okay, so that is how we write sets. So in roster form, where all the elements are listed individually. If there's too many to list all of them, then we would put ... to show that they continue forever. And then we have this set builder notation where we use a rule, a statement, or a formula in order to describe the elements that make up the set. Okay, then some more definitions. So here we have the definition of an empty set. Okay, so what is an empty set? So this is a set that does not contain any elements. So this is also called a null set. And this is denoted using phi. So this is a Greek letter, so it looks like a 0 with a line drawn through it. Or you may see set braces with nothing in between. Okay, so some sets do not have elements. That does not mean they are not sets. They are sets. They just do not have any elements. And these are the two symbols we use to denote them. So now something to take note of. Take note that phi is not the same thing as this. So these two sets are not equal because this set here is not empty. It contains the number 0. So 0 is an element of that set. An empty set does not have any elements. So if a set has 0 in it, then it is not empty. Okay? So these two are not equal. This is also not the same. So we can have a set within a set. So this set here contains the empty set. The set is not empty, okay? It contains an empty set. So you must think of it like a box, and inside that box you put an empty box. The original box, the one on the outside, is not empty because it contains a box, even though the box it contains is empty. Okay, so elements of sets are not always just numbers, letters. Even sets may be elements of other sets. So when we talk about power sets, you look at and understand more that sets can also be elements. Okay, so if you think about it like a box, usually I use a box to put things in, but you may have boxes whose elements are just other boxes. Okay, so maybe if you think about it in that way, then it would make sense. Okay, then we have what we call a singleton. So a singleton, this is a set that contains only one element. Okay, yeah, before that, I should also mention another example of an empty set is a set of NUST students younger than 5. Okay, so this set here is empty because there are no NUST students that are younger than 5 years old. So it is a set because it is well defined. If I give you a student, you will be able to tell me whether they belong in the set or not. You'd say, okay, are they a NUST student? Are they younger than 5? Then they belong to the set. But because there is no such student, then the set is empty. Okay, back to a singleton. So a singleton contains only one element. So some examples of the set. So we have A is equal to x such that x squared is equal to 0. So if you were to solve this, x squared is equal to 0, the only solution is that x is equal to 0. So this set here, A, contains only the element 0, and that is why this set here is a singleton. We have another one, B. We have x such that x is a natural number and x squared is equal to 4. Okay, so if you have this equation, x squared is equal to 4, and you solve it, there's obviously two real solutions, -2 and +2. But there is a condition here that x must be a natural number. So of the two solutions, -2 and +2, only 2 is a solution that fits this criteria. So this set contains only the number 2, and therefore it is a singleton. Then we have what we call finite sets. So this is a set that contains a definite or a specific, means a definite or a specific number of elements. So an example of this, we have A, this one here. Okay, so this set contains only one number or one element. That means it is finite. So I know exactly how many there are. It is specific. Okay, so this is our finite set. Okay, then empty set. The empty set does have a specific number of elements. It has 0, okay? Because I can say how many elements exactly it has. The empty set is finite. Another set C, we say X, such that X is a natural number and X plus 2 is equal to 5. So if I were to solve this, X is equal to 3. So that means this set C has only one element, okay? And that element is 3. It has one element that is a definite. It is a specific number. So that set C is finite. Then I have another set D, which is A, B, C. It goes on up until X, Y, and Z. So these are just the letters of the alphabet. And D, we know, has 26 elements in it. And 26 is definite, 26 is specific. And that is why we would say that D is finite. Now, the opposite of that is, of course, an infinite set. So this is a set containing never-ending elements. Okay, so they never end. We cannot state specifically how many elements we have in that set. So we have the set of natural numbers, of course, the set of real numbers, the set of rationals, the set of irrationals. We have our complex numbers, and there is so many sets that are infinite. Okay, even a set like this, A, such that X is a real number and X is between 0 and 1, okay? So if you look at all the real numbers between 0 and 1, there is an infinite number of them, okay? So even this set here is infinite. Right, then we've defined a set. We know what a set is. We know what elements of a set are. We know how to represent our set. And now the next thing is, what can we do with these sets? Can we compare them? How do we compare these sets? So the first way of comparing sets is by looking at what makes sets equal. So we talk about equal sets. So we say that two sets are equal, and we write A is equal to B if they have the exact same elements. So that means if I look at the elements in A, they are all in B. And then if I look at all the elements in B, all of them are in A, then we would say that the two sets are equal. So for example, if we have A is equal to 1, 2, 3, and B is the set of natural numbers less than 4. Then here we can see that these two are definitely equal. A is equal to B. Because if I were to list or write down B in roster form, the natural numbers less than 4 are just 1, 2, 3. So 1 is here, it's there. 2 is here, it's there. 3 is there, it's there. And if I look and write down all the elements here, I would find them here. Okay, so another one, this is example number 2. Let's say A is equal to the empty set, and B is this set. X is a natural number such that x squared plus 1 is equal to 0. So the empty set here, it has no elements. And this one here, if we're looking for natural numbers that when we substitute them here, the answer is 0, there are no such natural numbers. So B is also empty. So in this case as well, A is equal to B. Okay, so that is equality of sets. Then we talk about subsets. Okay, so sub, I'm sure you know already, means a part of something. So when you talk about subgroups, subregions, sub of something, it comes from a bigger one. Okay, so a subset, we denote them. So these are denoted by the symbol. It looks like a C with a line underneath. And then we say A is a subset of B if all the elements of set A, if all the elements of set A are in set B. Okay, so it's a subset. That means every element that is in A is also an element in B. So we can see some examples of subsets. The set of natural numbers. This is a subset of the set of real numbers because every natural number is also a real number. So if I pick a natural number, it will also be here. Okay, the set of rational numbers. This is also a subset of the set of real numbers. The set of integers. This is a subset of the set of rational numbers, and there's so many different subsets. Okay, then we can say A, this is countries in SADC. And B, we have countries in Africa. Okay, so here we can clearly see that A is a subset of B because every country that is part of SADC is a part of Africa. So that is a subset. Okay, so another one, we have a set A, which has 2, 4, and 10. And we have a set B, which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is clear here that A is a subset of B. Okay, now something to take note of with this subset. So take note that if we have A is a subset of B, and likewise B is a subset of A, then A is equal to B. Now, this is actually the formal definition or the mathematical definition of equality of sets. So two sets are equal if and only if they are subsets of each other. Okay, so what that means is if I give you two sets, A and B, and I ask you, are these two sets equal? I'm not necessarily asking you, you don't have to like physically, individually check every single element. One is here. They may have millions of elements. All you need to do is prove that if I pick an element in the first set A, I will also find it in the set B. And if I pick an element in set B, I will also find it in A. That means they are subsets of each other and therefore they are equal. Okay. Another thing to take note of, so this would be number 2, is that every set is a subset of itself. Okay, so we say A is a subset of A. Every set is its own subset because, again, with this, we should think of definitions, what a subset means. A subset means if I pick an element here, it's there. And if I pick an element from A, then that element is in A. That means A is a subset of itself. You could think about it like divisible by, every number is divisible by itself. So in the same way, every set is a subset of itself, and that's why it is equal to itself. Okay, and then another thing to take note of is that the empty set, which we call phi, or the 0 with a line in it, is a subset of every set. Okay, so think about it like the way we do with the number 1. The number 1 is a factor of every number. So in the same way, the empty set is a subset of every set. Okay. Now, the way we prove this, or how you must actually think about it in a mathematical way, is if I have two sets. So I have a set here. I have A and I have a set B. And I want to show that A is a subset of B. We said I must show that if I take an element here, then it's also here as well. Now, if I wanted to show that A is not a subset of B, then what I need to do is I just need to find an element here. It's in A, but it's not in B. That means A is not a subset of B. Okay, so again, if I want to show that A is a subset of B, I pick an element in A and show that, okay, there it is. It's also in B, and that applies to every element. Now, the other way around, if I want to show that A is not a subset of B, all I need to do is give an example of an element. It's there in A, but it is not in B. And that is how we prove that the empty set, sorry, I said element here. It should be subset. It's not an element. This is a subset. Okay, so the same way I prove that the empty set is a subset of every element, okay? So the empty set has no elements. So I can't necessarily use this argument that if I pick an element in the empty set, then it is in A. So I look at the other way around where I say, okay, can I find an element in the empty set? It's there, but it's not in set A. And because the empty set is empty, it is not possible to find an element that is here, but not here. That means the empty set is a subset of every set. Okay, so think about that, and we will continue in our next class.